Okay, so we're going to do the bonus questions now. I'm just moving them over to this screen. All right, hopefully you guys can see this pretty well. Okay, now for number 4, I do think I confused you guys because I stole this. Now if you watched the first video, I stole this out of a graphic out of the Regents. So I'm going to do this as one video. If you are bored with me and you want to fast forward, that's fine. If you if you didn't if you only wanted to watch the bonus questions, that's fine. So we're going to do all 3 of these in one shot. Okay, so first one, calculate the pressure if the gas in container A is cooled to standard temperature. Okay, but I'm assuming that because I didn't give you any information about the volume, here's the volume, pressure, and temperature. What was nice about this question, why I liked it, is it had all the variables lined up for you already. Is everything's here, P1, V1, T1's here. So that would mean that my T2 is just standard temperature. Okay. And I would assume that the volume's staying constant here. Now, this was me just writing a question really quick, so I wasn't really paying attention. But yes, I meant for you to say that you're holding the volume constant. If you're holding the volume constant and you have nothing but pressure and temperature, that would mean that this is Gay-Lussac's law. So I'm going to do what I've always do. P1 V1 over T1 equals P2 V2 over T2. I write the whole formula. 2 reasons. One, if I did it every time I practiced, I would memorize my formula. So that's a fluency goal. And 2, I really want to make sure I look and check to make sure I'm plugging everything in correctly. Okay, so I'm going to go ahead and take, I'm going to go ahead and take volume out of this equation. So once I take volume out of the equation, I have only pressure and temperature. That's Gay-Lussac's law. So I'm going to go ahead and plug in my pressure and my temperature. So 101.3 is my starting pressure over 298 is my starting temperature equals, I am calculating a new pressure. So P2 is my variable, okay, over a new temperature, which is 273. Okay, when you have 2 fractions set equal to each other is the only time you can cross multiply. I'm going to go ahead and cross multiply in an orderly fashion. Very low on entropy, okay? We're going to go, you can do either way. Shall we go the other way this time, you guys? We'll be wild and crazy. All right, ready? We're going to go that way first. So the number that goes first, I'm going to put that there. Then I'm going to go the other way second. Okay, the number that goes that way goes here. So this one's 298 P2, right, times P2. And this one on the other side, I skipped ahead because I didn't want to stop and put it in the calculator, but we will. Is 101.3 times 273 is 27,654.90. .9. Okay, same as I have been doing over and over again. I want to get P2 by itself, so I'm going to go ahead and divide both sides by 298. Okay, and just in the background, I don't think you can see the calculator pops up as a separate window. I'm going to do 27,654.9 divided by 298, and that's going to get me 92.8 as my new pressure. In kilopascals. Now, I'm going to think about it for a second. There's a direct relationship between pressure and temperature according to Gay-Lussac's law. So if my temperature went down, my pressure should go down. And it did. right? My pressure went down to 92.8 from 101.3. So it all works out. Let's clear that. Now for question 5, calculate the temperature of the gas container A if the pressure is raised to 150.2 kPa and the volume is decreased to 500 milliliters. So this is my second set of variables. So I'm going to go ahead and write those down, T2, V2, and T2. Okay, I'm going to calculate the temperature. So T2 is my X. If the pressure is raised to 150.2 kPa is my second pressure. My volume is 500 milliliters. It looks like my pressure went up and my volume went down. So I'm expecting that my temperature, I don't know what my temperature would do under those circumstances. I made too many changes at once. All right, so I'm going to go ahead and write my formula because that's what I should always do. I need all the variables this time. So I'm going to go ahead and start plugging in. 101.3 is my first pressure. My first volume, 750. Okay, my first temperature, 298. Over here, my second pressure, 150.2. My second volume, 500. And last but not least, I'm going to solve for T2. Okay, I'm going to go ahead and go this way first, cross multiply. So I'm going to do 101.3 times 750. 75,975. T2. Don't forget your variable. You're not going to know what to solve for. Now I'm going to bring my equal sign down. Make sure I keep track of my work. And then I'm going to cross multiply in the other direction. Okay, 298 times these guys. Now you can do, because of multiplication is, because of the multiplicative property, that means if everything's being multiplied, it doesn't matter what order you're multiplying in. But if you were to have more than one operation going on, then you have to be careful that you follow a sequence, and the sequence usually is PEMDAS, right? Parentheses, exponent, multiplication, blah, blah, blah. Okay, but in this case, 298 times, these two are being multiplied, and these two are, and it's multiplied by 298. So I can just multiply everything in one shot. But make sure if you're using a scientific calculator, you actually have to put it in as 298 times 150.2 equals, then get a number, and then times that number by 500. And it is an enormous number, 22,379. Comma 800. It's a really big number. Okay. I just made up numbers at 5 o'clock in the morning. I wasn't really thinking about it, you guys. Sorry. Okay, so 22,379, comma 800. There's a decimal here, right? Then my algebra says I'm supposed to divide both sides by 75,975 to get T2 by itself. I will also bring down this incredibly large number. To 294.56. Which is a perfectly good temperature in Kelvin, right? 294 is a perfectly reasonable number. You were at 298. Apparently, you just brought the temperature down by 4 Kelvin. All right, last one. Assuming a container is capable of expanding calculate the volume of the gas in the container A if the temperature is increased by 350 and the pressure is decreased by 50 kPa. So again, this is a full 3-step problem. Okay, the only shortcut I'm going to take right now is I'm going to label this as temperature 2, and I'm going to go ahead and label this as pressure 2, and I'm going to look at my question to find out what I'm solving for. I am solving for V2. So I'm going to write out my formula, P1 V1 over T1 equals P2 V2 over T2, right? I'm going to go ahead and say I am solving for V2, so I'm going to circle it, and then I'm going to start substituting. So 101.3 times 750 over 298. Did I make a mistake before you guys and plug in 50 instead of 750? I might have done that. I don't know. I had such enormous numbers. It's hard to believe I did do that. Oh, maybe I didn't have to use volume? No, I think I plugged in. All right. If I did do that, I apologize. Everything else was right. The algebra was right. All right. And then pressure 2 is 50 kPa times volume 2. I don't know. I'm solving for it. And temperature 2 is 350. Okay. So 101.3 times 750 times 350 is my first move. Or I could go the other way. Let's live dangerously yet again. We'll cross multiply this way first. Okay, so that's 101.3 times 750 times 350. 101.3 times 750 equals, and then in the calculator, when you get an answer, then do times 350, unless you're using a graphing calculator. Now you can do this, well, no. Yeah, it's just you have to, if you're doing it in a graphing calculator, it might let you do all 3 terms at once. But on the scientifics that we have at school, you can't do it that way. You have to let it find an answer for the first 2 and then multiply the third one. All right, times 750 equals 75,975 times 350. Ooh, this is going to be a big number. That's 26,591,250. All right, so 26,591. Oh, I'm suddenly realizing why they use small numbers in these calculations. Equals. Now I'm bringing my equal sign down. Make sure I don't mess this up and I get it in the same order. I'm going to go ahead and do my cross multiplication in the other direction. Okay, that's 298 times 50 times V2. Which is 14,900. Okay, this is 14, divide both sides by 14,900. Most of what you're going to have trouble with is just making sure you consistently keep track of everything and stay focused through the whole thing so that you don't drop numbers or make silly mistakes. So 26,591, 250 divided by 14,900. Now, if you're good with your calculator, oh, that seems wrong. What did I do here? That number seems way too big. Okay. Oh, I dropped the pressure really severely. That might be why it's so weird. Okay. I think because I dropped the pressure so much, the volume expanded a lot. Okay, that makes sense because if volume and pressure are going to go down somewhat proportionally, I cut the volume. Sorry, I cut the pressure in half. So this really would have been able to expand a lot, and it's already at 750 milliliters, so I'm probably not wrong. All right, let's do the math one more time. 26,000. Look at that. This is an example of even me getting freaked out by getting a number that's too big. 14,900. Yeah, 1,784 is what I'm getting. And other people definitely didn't get that answer, I feel like, when we did this on the boards. Um, so either there's a mistake in my math somewhere. I am using that like little pop-up calculator that's on the computer, so I could have just keyed it in wrong. Let's do it one more time. 101.3 times 750. I think this would be better if it was done in liters. Times 350. It's 26,000, blah, 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 blah. Divided by, yeah, it is. It's 1,784.6. Ooh, that was a big number. Did we really get that in class? I don't think we did. We might need to talk about this when we reconvene tomorrow before the quiz. All right, you guys, that's the last question. So I'll see you tomorrow for your quiz if you're still watching. And I'll work on making better videos. All right, I'll see you tomorrow.